Today we're going to talk about exponential equations. Now, really I should say that this is exponential equations part 2. If you remember earlier on in the unit, like day 2 or 3 or something, I talked about exponential equations before, but if you remember, I called those simple exponential equations, and I might have made a comment that the procedure I outlined at that time only worked for certain kinds of exponential equations. Today we're going to look at harder exponential equations. In these equations, the method that we used earlier does not work. So let me just remind you, first of all, what that earlier method was. Suppose you have an exponential equation like this. 4 to the x is equal to 8 to the x minus 1. So first of all, let's just recall, why is this an exponential equation? The reason why is the variable is inside of an exponent. That's what makes it an exponential equation. Now, this is an equation of the type that we learned how to solve earlier in the unit. The trick was to basically, if you remember, recognize that 4 and 8 are both powers of 2, and then to rewrite each of those using that information. So 8 is 2 to the third, and then you can just sort of use power of a power rules to get 2 to the 8 is equal to 2 to the 3x minus 3. And now you have an equation of the form 2 to the blah equals 2 to the other blah. And if you remember how this goes, you can now set the two exponents equal to each other. And then you can solve from there. I won't bother finishing the whole thing, but that's the equation. That's the kind of equation we learned how to solve earlier in the unit. Today we're going to look at a different kind, where this procedure does not work. So, and basically the procedure, the technique is to use logarithms. So let's consider the first example. 2 is equal to 3 to the x. So this is an exponential equation. The variable is inside of an exponent. But if you compare this equation with this one, you can see there's something fundamentally different. Namely, the numbers here, 2 and 3. 2 and 3 are not common powers of the same thing. 4 and 8 are. They're both common powers of 2. But 2 and 3, no, not so much. So this whole procedure just won't work for this equation, and we have to do something else. The something else that we have to do is use logarithms. Now, technically, there's a lot of different ways of doing this. So the big idea is you're going to take a logarithm of both sides of the equation. Now, when I say take a logarithm, you're actually free to choose the base. You could take logarithm base 3 of both sides, or you could take logarithm base 10 of both sides, or you could take the natural log of both sides. It'll all kind of work out the same. Sometimes one choice is better than another. I think that what I would like to do is to always take the natural log of both sides. It's not the only choice, and it's not always the most efficient way of doing things, but there are some very good reasons to make a habit of using the natural log over any other kind of logarithm. So what I'm going to do is I'm going to take the natural log of both sides of this equation. Now, when you first look at it, it seems like I've kind of made things worse, but here's what you have to do. You have to remember that there is this log law, a rule about logarithms that we talked about a couple of lessons ago, and it says the following. I'll remind you what it is. It says log base b of a to the x. So if you have an exponent inside of a logarithm like this, then that exponent can actually be pulled out and put on the side. That is the same thing as x log base b of a. And it is that property that really allows us to solve this equation. Because if you look at what you have here, you have an exponent, x, inside of a logarithm. And this rule here tells you that you can actually just take that exponent and pull it out and put it on the side. So I'm going to go ahead and do that. So I have natural log of 2 is equal to x times natural log of 3. This is no longer an exponential equation because the variable is no longer inside of an exponent. So that's good. Now, you're probably looking at this and you're like, oh my god, that's a whole lot of letters. Like, how do I solve that thing? Believe it or not, this is actually a linear equation. Okay? Natural log of 2, as complicated as that looks, it is just some decimal. Okay? And natural log of 3, as complicated as that looks, it is just some decimal. You know, natural log of 2 is like, actually, I don't know. What is it? It's like 0.693. And natural log of 3 is some other decimal. If you wanted, you could ask your calculator right now, what are these values? And you could replace those two expressions with their decimal values, and you'd have a linear equation involving decimals. You certainly know how to solve that. But here's the thing. Natural logs, for the most part, are irrational numbers. If you ask your calculator for natural log of 2, it's going to give you a decimal approximation. Okay? It's going to, and obviously you're not going to write down all infinitely many digits of this thing. You're going to stop somewhere, which means if you replace these expressions with the value you get from your calculator, you're not getting an exact answer. You're actually getting a rounded answer. I would like an exact answer, okay, which means rather than replacing these two expressions with their decimal approximations, I'm going to leave them as they are, okay? And, you know, to solve this equation exactly, all I have to do is get the x by itself, all right? How do you get the x by itself? Look, natural log of 3 is just a number. This is like x times some number. How do you get the x by itself? Just divide both sides by natural log of 3, okay? And that'll get the x by itself. So I find natural log of 2 over natural log of 3 is equal to x, okay? And that is an exact answer. Now, tomorrow we'll see that this expression can actually be simplified a little bit and written in kind of a nicer way. But for right now, that's good enough for us, okay? All right, so let's do another example. Let's have a look at... here's the next one. 3 to the x is equal to 7 to the x plus 2. Okay, so once again, 3 and 7, these two numbers cannot be written as common powers of the same number, which means the old method that we used earlier in the unit will not work. We must use logarithms. You have to take a log of both sides. There's some argument that taking the log base 3 of both sides would make sense, or that taking log base 7 of both sides would make sense, but I'm going to continue to just take natural log every single time. It's my favorite log, and it should be yours too. So I'm going to take the natural log of both sides of the equation. Okay. At first, this looks worse, but then you remember, oh, there's this rule about logarithms, which says that if you have an exponent inside of a logarithm, then you can just like pull it out and put it on the side as an outside multiplier. So that's what I'm going to do to this x right here. That's going to go on the side. And this exponent here is also going to come out and go on the side. So I have x times natural log of 3 is equal to, and now I'm going to be very careful. The exponent here is x plus 2. That entire exponent is supposed to become a multiplier on the left of the natural log. A lot of students, when they first try this, what they do is they say, okay, x plus 2, I'm going to pull that out and put it on the side, and then I've got the natural log of 7 left over. As it is written, that is incorrect. And the reason why is that the entire exponent, x plus 2, is supposed to be multiplying natural log of 7. As it's currently written, only the 2 is multiplying natural log of 7. Only the second term of that expression. You want this entire exponent to be multiplying natural log of 7 when it comes down. And in order to make that happen, you have to use parentheses. Okay, that is correct. Don't make that mistake. It's very common to make that mistake. All right, now, once again, I want to say you could, at this point, take out your calculator and evaluate natural log of 3 and natural log of 7, get some decimal approximations, replace those expressions with their decimal approximations, and it would be a linear equation with some decimals, and you can definitely do that on your own. However, that will not be an exact answer, because whatever you write down for these two things is going to be a decimal approximation, because these are irrational numbers. So I want an exact answer, and the way that so in other words, I have to leave natural log of 3 and natural log of 7 as they are. I cannot replace them with a decimal. Now, I still have to solve for x. A lot of people look at this equation and they're like, I have no earthly idea how to solve for x. The truth is, you actually do know how to solve this equation. You just don't know it yet. Look, I'm going to put this equation on hold. Okay, I'm going to pause. And I'm going to write down a different equation. Okay, similar to this one, but different. Here's the different equation. X times, let's say, 8 is equal to x plus 2 times, let's say, 9. Do you think that you can solve this equation? Yeah, you definitely can. What you should do is distribute the 9, right, to these two things here. So x times 8 is equal to 9x plus 18. And then if you notice, you've really got, I mean, this thing right here is really an 8x. Maybe I should rewrite that. That's 8x equals 9x plus 18. And then hopefully you should say to yourself, oh, the problem here is that I've got x's on both sides of the equation, and I need to put all of the x terms on one side. So I guess I'll subtract 8x from both sides. So I get 0 is equal to 9x, take away 8x is 1x. So that would be 1x plus 18, and then you can solve from there. It's pretty obvious. Now, what I claim is that the steps that I've taken here in solving this equation are essentially the same steps that you need to take to solve this equation. Why? The reason why is that natural log of 3 and natural log of 7, even though they look fancy and complicated, are in fact just numbers. Okay, the way that you solve this equation, look at the structure of this equation and compare it to this one. Notice that the two equations are identical, except instead of natural log of 3, I've got a much more conventional, familiar number, 8. And instead of natural log of 7, I've got a much more conventional, familiar number, 9. Okay, but structurally the equations are the same, and so therefore the steps that you have to undertake to isolate the x are identical. All right, so you have to bear that in mind. So whenever you look at an equation like this and you get stuck and you're like, I'm not sure how to push stuff around, I don't know how to get the x by itself, what you should do is imagine that these natural log terms are just regular numbers. And ask yourself, what would I do if they were just regular numbers? And then you have your answer, okay? So, all right, so let's just implement these steps here. So very similarly to this equation here, you know, natural log of 7 is just some number multiplying the x plus 2. It needs to be distributed, right? It needs to be distributed to these two terms just like the 9 was distributed here, right? So let's go ahead and do that. So I'm now working on my actual equation that I care about, not the toy equation that I wrote here. So, all right, so distributing the natural log of 7, I have x times natural log of 3 is equal to, all right, so natural log of 7 times x is natural log of 7x plus, and then 2 times natural log of 7 is, I guess, just 2 natural log of 7, okay? Now, at this point, you're like, oh, I don't know what to do. You know, I don't know how to solve this thing. We are essentially at this stage of the equation, right? Or maybe, if you like, perhaps this stage. These two equations are pretty much interchangeable. If you look at this equation, you know, structurally, it's very similar to where we are here. X times a number, x times a number. 9 times x, you know, a number times x, right? Very similar structurally. And then 18, that's just a number. 2 natural log of 7, that's just a number. What did we do here? What we did was we put everything on one side, or we put all the x terms on one side, right? We were like, oh, we've got x terms on both sides of the equation. We'd better move all the x terms to one side. So that's what I'm going to do. I'm just going to move, you know, you could move them both over to the left, or you could move them both over to the right. It doesn't matter. I'll move them both over to the right. Why not? So I'm going to subtract x natural log of 3 from both sides. So I have natural log of 7x minus x natural log of 3, and then I've still got that plus 2 natural log of 7, okay? Now here's the thing. These two guys right here, you know, that is a lot like our 9x take away 8x, right? But when I subtracted 8x from both sides in this equation, you know, I implicitly combined the two terms. 9x take away 8x is 1x, right? And I like combined the two terms. 9x minus 8x, I combine them into a single term. That's what I have to do here. I've got something x minus something x. I need to combine those into a single term. How do you do it? Basically, x is a common factor, and you need to pull it out. If you pull out the common factor of x, here's what you get. So I'm going to remove the x, okay? What's left over if I pull the x out? I have natural log of 7 minus natural log of 3. And then I've still got this term here, the 2 natural log of 7. Okay? So, you know, now we're basically at this stage, believe it or not. Because if you look at what we have structurally, it's a number times x plus just some number. It's a linear equation. How do you solve it? Well, first you should move this thing to the other side, right? So I'll just subtract that from both sides. Negative 2 natural log of 7 is equal to natural log of 7 minus natural log of 3 times x. And then how do you get the x by itself? Well, look, this is a number multiplying x. How do we get rid of that number? You have to divide both sides by that number. So you divide both sides by that expression, and you get negative 2 natural log of 7 over this whole thing in brackets. That's natural log of 7 minus natural log of 3 equals x. And that is an exact answer. Okay? Pretty tough, but you'll get used to it. If you know this kind of topic, if you know this topic really well, you're probably looking at this and you're saying, that is definitely not the simplest way of expressing the answer. I know that, but I want to postpone simplification till tomorrow. That involves change of base, which we'll get to later. Okay, so let's just do another couple examples here, and then we'll be done. So consider the following exponential equation. 4 times 5 to the x is equal to 6 to the x. So just like before, we're going to take the natural log of both sides. So I have natural log of 4 times 5 to the x is equal to natural log of 6 to the x. The reason I'm doing this example, it is very tempting to look at this and say, oh, I've got a variable inside an exponent, inside a logarithm. Maybe I can just take this x out. You actually can't. Basically, the rule that you're trying to use is the following. It says that natural log of, let's say, a to the b is equal to b natural log of a. The trouble here is that in this rule, which you're trying to apply here, it is the entire inside of the logarithm that is being raised to the power. Not just part of it. Not just a factor, but the entire inside of the logarithm is being raised to that power. Only then is it true that the power sort of can be pulled out and put on the side. If you look at our equation here, it is not the entire interior of the logarithm that's being raised to the x. This x is only affecting the 5. It is only the 5 which is being raised to the x. And so therefore, this rule just doesn't really apply. What you can do with this equation is you can use the other log rule, because fundamentally what you have inside this logarithm is a product, 4 times 5 to the x. So you can rewrite that as natural log of 4 plus natural log of 5 to the x. That's using the other rule of logarithms. Over here, I actually can pull this x out. So I have x natural log of 6. All right, so now looking at this natural log of 5 to the x, now that it is the entire natural log, or the entire interior of the natural log, which is being raised to the power, now I actually can pull that x out. So I have natural log of 4 plus x natural log of 5 is equal to x times natural log of 6. All right, so now, as before, this looks like a complicated equation, but actually it's a linear equation. Natural log of 4, 5, and 6, those are just decimals. So what do? Well, you need to bring all the x terms over to one side. So I'll subtract this term here from both sides, giving me natural log of 4 is equal to x natural log of 6 minus x natural log of 5. At this point, it's maybe less clear what you have to do. The trick is to factor out the x from both of these terms. So I have natural log of 4 is equal to x times natural log of 6 minus natural log of 5. And now, finally, I can solve for x by dividing both sides of my expression by, or both sides of the equation by this expression. So I have natural log of 4 over natural log of 6 minus natural log of 5 is equal to x, and that's an exact answer. Cool. All right, one more example, and then we're done. So let's have a look. So my last one, this one won't be very long. So here's my equation. E to the x squared plus 1 equals 5. So you could try to take the natural log of both sides right now. That would be a mistake. I'll just show you what happens. You get this. Unfortunately, this expression on the left just cannot be simplified in any useful way. The natural log of a sum, there is no rule for that. Like, there's no rule for natural log of one thing plus another. So this doesn't work. The obvious, or maybe not so obvious, the better thing to do is to subtract 1 from both sides before taking the natural log. So you have e to the x squared is equal to 4. Now take natural log. Okay. Great. Okay. This one's going to work out really nicely. You can think to yourself, oh, this is the natural log of e to the x squared. Remember what this means. This is the power of e, which gives you this expression. What power of e gives you this expression? Well, x squared. Alternatively, you can think of it as you're exponentiating by e, and here you're taking the logarithm base e. Those two operations cancel each other out, and you're left with just x squared. And that is equal to natural log of 4. And then, yeah, we can now just take the square root of both sides to get x is equal to plus or minus the square root of natural log of 4. And those are the exact answers.